Hi everyone. In this video, we're gonna see, we're gonna continue our tour of the electron transport chain, and we're gonna go into more detail on what happens to Q, coenzyme Q, that reduced. It received the electrons from complex 1 or complex 2, and now the job of complex 3 is to take the electrons from Q and pass them on to cytochrome C. So let's see how that happens. So the overall reaction is like this. We have a coenzyme Q that's reduced. It picks up two protons from the inside. And overall, as you will see, we're going to have four protons on the outside. Coenzyme Q gets oxidized, and the electrons go on to cytochrome C. So two molecules of cytochrome C are going to be reduced. The redox reactions of cytochromes use just straight up electrons, not protons. So oxidation of coenzyme Q, the ubiquinol form of coenzyme Q, is a net acidification here. Complex 3, yeah, let's just move a little bit. Looks like this. Again, there's the membrane, and this is the outside, that's the inside the matrix, and you see the overall reaction at the bottom, and you have a scheme of how that works. This is what you see in many textbooks, but we're going to do this in detail because it's actually quite complex, and we'll see how that works out. So we get the exact stoichiometry shown here at the bottom. The key point is again that Q is in the lipid bilayer. Okay, it's really embedded in the membrane. Cytochrome C is on the aqueous phase of it's close to the membrane, but it's on the aqueous phase of the just outside of the inner mitochondrial membrane. So these are very important little molecules, okay, that we're talking about here. Just to remind everyone what Q looks like. Again, we have the fully oxidized form and one electron at a time. You have the semiquinone if you pick up only one electron, and then going from the semiquinone to ubiquinol, where the keto carbons essentially have been converted to hydroxycarbons. Then there's going to be another electron involved, and here we also have protons when the hydroxy group is ionized. All right. So again, how do the energy so that's the reduction. Okay. So here in our discussion, we go in the opposite way. Okay. So we have reduced Q, and which we got from either complex 1 or complex 2. Okay. This is what complex 1 and complex 2 do. They pass their electrons on to Q, and now we're gonna go from right to left, and we'll see how Q gets oxidized, and that's a job of cytochrome 3, of complex 3, sorry. All right, so at this point, let me share a different screen so we can actually do the scheme on the board, because I think it will make more sense. So let's do that. Oh, not so bad. All right. So let's see. We start, we have our membrane. So that's going to be outside, that's going to be in. That would be the P side of the membrane, and that would be the N side of the membrane. And we have, let's start with two reduced Qs, okay, two ubiquinols. And let's start with one of them. One electron is going to come off. And it's going to find some iron sulfur cluster. This is all on complex 3, okay, the iron sulfur clusters and all that. It's going to find cytochrome C1. So the electron goes through those and eventually gets to cytochrome C, which is in the aqueous phase of just outside of the membrane. Um, and what will happen to one ubiquinol that got reduced? It's going to be in this intermediate, the semiquinone that we have described in the previous slides, and that will lose one more electron and become Q, the ubiquinone, and the electron will go through, a couple other cytochromes, B, L, and B8. Now Q keeps moving. It's mobile in the membrane and picks it up again. Okay, and becomes again a semiquinone. And we'll leave it from now at this point. The other molecule of the quinol, it does exactly the same thing that it did on the left side. So we're going to have an iron sulfur cluster. The electron will go through that part of on complex 3 and reduce another molecule of cytochrome C. And something key that I forgot to mention is in each one of these electron transfers, 2 protons in each case will come out. So already we see that this electron transfer becomes, all these reactions actually generate proton motive force, okay, because there is a net transfer of protons from the inside outside. Inside meaning they were on Q and now they go away. So let's continue on this one. We got now semiquinone, and it does exactly the same thing that we discussed before. It loses another electron. It becomes fully oxidized in this case, and the electron goes through Bl and B8. Okay, and what happens to this electron? It's going to be picked up by the semiquinone Q from one of the original fully reduced quinols, and that will become now Q fully reduced and with 2 protons from the inside. It will become one molecule of fully reduced quinol. Now, ubiquinol. Now, if let's add everything up and see what what we started with and what we end up with through this reaction. This is the famous Q cycle. So if I doubt that if I had not drawn it, you could have figured it out from the slides of the book. So hopefully this is helpful to explain the stoichiometry again. So we'll start with here. Let me write this in with red so we can distinguish it. So we have 2 fully reduced Qs, and we got 2 protons from the inside. Let's call them in and out. Okay, so 2 from in, and we got the way this should have been written here. Let me just, this is going to be reduced cytochrome C. So of course it was oxidized. So the electron um, reduces each of the two cytochrome Cs. Okay. All right. So if we write this now, we have two oxidized um, cytochrome Cs. Okay. And for Qs, we got one oxidized and one fully reduced Q. We got four protons that came out. And of course, the two reduced cytochrome Cs. Let me just write this a little clearer, make it a little bigger. Oxidized, and it picks up the electron that came from one of the Qs and became reduced. So that's the stoichiometry, and now of course we can remove one of these things, and that's the net. All right. So this is the Q cycle. This is how it works. It was actually, these reactions, as you see them, were originally proposed by Peter Mitchell himself. Okay, and that explains the stoichiometry. Now let's stop this screen, and we're gonna return back to the slides. All right. So this is where we were. And this recapitulates exactly what I was drawing on the board. So we're not going to do this again. It illustrates, the different redox states of coenzyme Q. And what we do have again is one net oxidation of one fully reduced coenzyme Q. And the protons, we have a gain of 4 protons on the outside and a loss of 2 protons on the inside. So it's actually a very significant generation of electron motive force, of proton motive force, I'm sorry, proton motive. And all these protons, as we saw also with complex 1, they move and they stay on the outside. What will happen if the membrane leaks? Okay, what is that's going to happen? The electrons will keep moving, but you won't build any proton motive force. You will not charge the membrane, and there are compounds that will do that. Okay, DNP is one of them shown here, and you don't generate a proton gradient. All right, you continue to respire up to a point, and then you don't generate gradient, which means you don't make ATP. Now, wouldn't that be great? For example, to this essentially you don't make ATP, you don't store your energy, so you keep eating the food and it just burns into heat essentially. And so such compounds could be used, for example, as an anti-obesity medications. In fact, they had been used like that. They had FDA approval in the 30s and 40s, in the 30s mostly, to be used. So these uncouplers, as they are called, they had FDA approval to be used for obesity and diabetes. By the way, why uncouplers? Because it uncouples the electron transport chain, which normally is coupled to ATP formation because you generate this proton gradient, but you uncouple ATP formation from the proton gradient if you have a hole essentially in the membrane that allows the protons to go through, right? So that's why they're called uncouplers. So, but then they were banned. Sorry, to go back to what happened to these compounds. So we use them in the research a lot. Okay, they're called ionophores, uncouplers, and but not in clinical practice. But there might be a comeback if properly low doses they can be used. And it turns out they can be used in rodents here, and very controlled. Okay, really not overdosing on those things, because then you cannot produce any energy, so you cannot breathe essentially. Um, that's what they were causing. They were causing heart attacks, and that's why FDA pulled them. But in a controlled manner, if you release little by little just these drugs, it turns out they can reverse diabetes even in rodents. So who knows? Maybe there is a future to this uncouplers in clinical practice again. So, but that summarizes what I had told you. This is the overall equation that we saw how it gets derived through the electron transport chain um, at complex 3, and we saw how this comes about. Um, the next reaction now, the job will be to take cytochrome C, and that's complex 4 now, and oxidize cytochrome C, take the electrons and put them onto oxygen. This we will discuss in the next video.